Hello everyone, welcome back to Real Time Systems. My name is Renuka, Assistant Professor in Department of Electronics and Communication Engineering, Maharaja Institute of Technology, Mysore. In previous class, we had studied about what do you mean by digital signal processing, and we also dealt about what is a digital input interface and output interface along with the pulse interface, correct? So we also understood what are the different kinds of pulse interface that could be accommodated in any of the plant or in a processing unit. A pulse interface is nothing but a bridge which is between processing that is the central processing unit as well as the plant, correct? So we also dealt about the three different ways in which the pulse stream could be given as an input. Okay, the first will be the continuous, wherein you have T on and T off being uniform. Okay, and the second would be the variation in the length of the pulse, and the third will be the pulse width modulation. Let us understand the different types of these pulse interfaces. So let us consider the first type as a series of pulse of a fixed duration. So fixed duration, if you remember, we had also dealt about what is a clock, correct? Clock pulse. Whenever you have a clock to be initiated, then you have a T on and T off to be equidistant. So if I take 50% of the duty cycle is on, then 50% is off. So it is continuous, correct? So that will be your fixed duration. Okay. A computer turns a pulse generator on or off or loads a register with a number of pulses to be transmitted. So a computer turns a pulse generator on or off or loads a register with a number of pulses to be transmitted. The pulse output is sent to the processor and used to decrement register contents, and when the register reaches 0, the pulse output is turned off. For example, the movement of the stepping motor. So what do you understand by this? In type 1, you have a continuous stream of pulse which will be transmitted from the central processing unit to the plant, okay, in such a way that the pulse duration has information. Okay, let us consider. So you have these pulses. For example, if you consider pulse 1, pulse 2, pulse 3 are the three pulses that needs to be containing an information, okay, to switch on or off a system. Example, if I consider a stepping motor. So if you want to set it on for 3 pulses, then that information is sent from the central processing unit to the plant. Correct? So what happens there, you have these 3 pulses which will be sent, okay, from the interfacing, that is pulse generating unit to the plant. So as soon as it is generated, all the information is now transmitted from the pulse generator to the plant, and from the plant what do you have? You have the motor, the stepper motor being on for certain duration of time, and then again for the next pulse it goes off. And then what happens, this output of the plant, okay, when it, there is a decrement of these pulses. So it counts 1, 2, 3. So once 3 pulses are counted, what happens? The register content becomes 0, or the counter, I can say, will be off. Okay. So when the pulse generator counter output, okay, once is the pulse generator pulse output goes to 0, then what happens? The information is already been transmitted. Okay, so this is how actually your a complete cycle of pulse with a fixed duration is being studied. Okay, next we have the type 2, which is called as a single pulse of variable length. So single pulse, if I consider it switches on for few milliseconds and then it turns off for after couple of seconds. Okay, so if I take 3 seconds is an on duration and 1 second is an off duration, again I have a 3 seconds of on duration and 1 second of off duration. What will happen? A single pulse of varied length. Okay, the computer sends variable length pulses to the plant, and then it is typically used to operate process control valves. So this is a very small type or systems with a simple or a few inputs and output lines. So in this system, unless the pulses is on, the valve is open. Okay, then it turns off after, as a previous example quoted, we have 3 seconds. For 3 seconds you have the valve open and it closes after the 3 seconds. So what happens, then information will be transmitted from the computer, that is a central processing unit, to the plant through the pulse generator. So pulse generator will generate the pulse for totally about 4 seconds, okay, and then what happens, the action will be continued and the pulse counter will have a count. What happens in the pulse counter, it actually keeps the valve open for 3 seconds, and after 3 seconds, the 1 second, you have the valve being closed, okay. So this is the complete operation of a single pulse with a varied length or variable length. And we have what type 3. Type 3 is nothing but pulse width modulation, which is a special interface chip and is used to generate the pulses. This output is fast pulse width modulation stream will be produced and then converted into a linear analog output by using a low pass filter. So here again you have a variable pulse width modulation. We have already dealt about what do you mean by pulse width modulation, how it is applicable in previous module, right. So similarly, after knowing all these 3 types of the pulse interfaces, usually we adapt the first type 1 is mainly used for clocking, okay. It can be actually considered as a counter, okay, which will increment and decrement, okay. That pulse generated itself could be considered as a counter, clock counter, okay. So after knowing all these 3 types of pulse interface, let us move on to what is meant by an analog interface. Conversion of analog measurement to digital involves 2 operations. One is called as sampling, other called as quantization. So here you have conversion of analog measurement. What is an analog measurement? Okay. Analog measurements are the measurement which is continuous with respect to time. Okay. For example, okay, if I take voltage with respect to time, frequency with respect to time, pressure with respect to time, temperature with respect to time. So these are the different analog measurement, and that has to be converted to digital format, right. So that will be in terms of zeros and ones. And how can that be done? With the help of sampling and quantization. These are the 2 techniques, okay. So ADC consists of a sample and hold circuit on the input of the device, and it is being converted to a discrete quantity. So if let us just explain the whole concept of analog interface using a block diagram. If you just see this block diagram here, what do you see? You have a plant, okay, this is a plant, and you have a central processing unit. If you just check into all the block which comes between a plant and a central processing unit, you have a multiplexer, a sample and hold circuit, then you have analog to digital converters, okay, and you have certain paths that the control signals that will be generated from the CPU, and it will be connected to the multiplexer. So now let us try to understand the concept of this analog interface, okay. So you have a plant here and you have a central processing unit. Suppose if you want an analog signal, let us take an example of voltage, or you can say pressure, okay. So if a pressure is an analog signal, so that pressure is actually sent from a plant to a sample and hold circuit. So sampling is nothing but you are trying to make sure that those physical quantities are converted, okay, they have to be converted to desired voltage levels, okay. So after those desired voltage levels are obtained, that will be converted into digital zeros and ones, correct. So for that we have 2 different levels. One is called as a high level, okay, level signal, other is called as a low level signal. If you consider high level signals, it would be operated between 0 to 10 volts, and if it is low level signal, then you are being operating at a very low value, about millivolts, okay. So now let us try to understand how this process actually happens, okay. So analog input interface, the computer issues a start or a sample signal of 1 microsecond. So the 1 microsecond sampling is being done. It is nothing but breaking down of the entire signal into small pieces of signal, okay. It is like sampling with respect to time. In response to the ADC switches, the ADC switches is here, sample and hold. What happens? A sample for a short period, after which a quantization commences. So there is a sample and hold circuit here. What does it do? It will try to discretize or break the entire signal into small pieces of signal, and then those small pieces of signal, which could be of the order of millivolts, and then it could be further processed, okay, wherein you are holding the circuit for certain duration of time, okay, approximating the level of signals, okay, which is called as a quantization level. So then those two process happens at your after the analog and digital converters, okay. So what happens? The sample and hold circuit will have all the samples which has been discretized, okay, and then you have analog signal which are actually discretized, and you have a quantization level being fixed before it reaches your analog to digital converter, and this digital converted signal will be sent to the central processing unit through the input output interface, okay. These input output interface will level, we would have already fixed the level for ones and zeros, okay. So the input for this interface IO devices here will be zeros and ones, okay, that will be the data. But what happens is, when you have more number of interfacing units being connected, there will be a difference in sampling rates, correct, and you have different speed of operation. So in order to overcome such issues in before sample and hold, we have what is called as a multiplexer. So wherein you can instead of having one A to D converters for each and every interfacing unit that you're going to connect externally. For example, if you have some data being extracted from a plant as a pressure, then you have another analog signal which is taken as temperature, okay. If these two are the two different entities, then you need to have two ADCs, and then you have to have a converter. Instead, you have what is called as a multiplexer. This multiplexer is a block which is between the plant and the sample and hold circuit. What will it do? It will try to have n number of inputs, and it will it will compress all the signal to one high frequency signal, okay, and voltage signal, which will be sent to the sample and hold circuit. So from there you have sampling, okay, and slicing of the signal, okay, so that these information will be then converted into discrete digital data, okay, that is zeros and ones, the streams of zeros and ones, which will be interfaced in the IO interfacing unit, and then it will be sent to the central processing unit for its computation. So once it is done, then it goes back to the multiplexer, okay, and then you have the plant. So you have you need to have another D to A, because once you have analog to digital converter, you can just get the information. If you want to display the information and get the plant working, then you need to have a digital to analog converters, okay, wherein the system, the plant would be able to actually access zeros and 1-bit streams, which is obtained by ADC, okay. So after few milliseconds or microseconds, ADC raises a ready or a complete lining or pole, or use a generate a interrupt. So along with the processing, which shows that another peripheral device is ready to actually send the data or communicate to CPU, okay. So a multiplexer helps reduce expenses on having separate ADC for each analog signals that we have already dealt, right. So instead of having multiple such ADCs, we can just have one single ADC, but with a multiplexer being connected. It's a solid state device with a high level that is 0 to 10 volts. If it is solid state, then it will be for high levels, which will be operated at 0 to 10 volts, and for low level signals operating at a very low voltage levels, which is about millivolts, you can just have a programmable gain amplifier which can be used to mux. It can be used between this multiplexer and a sample and hold circuit. If you have a small programmable amplifier here, it would be easy for it to program and control all the sampling of data, okay, before it could be sent to the ADC, okay. So let us try to understand, once we have already got analog to digital conversion being done at the CPU, now we need to know what is your digital to analog. So we have to study about analog output system. Okay, what is analog output system? DAC, that is digital to analog conversion, normally provides one converter for each output. So if you just see this block diagram here, you have a plant, okay, you have a central processing unit, you have an input output interface. Okay, so what happens, the information which is already been converted into digital format, that is zeros and ones, should be now sent back to plant, correct? Because you have studied in the first class how a simple air blower is used, right? So you have zeros and ones, which will let the valve opening, closing, or turning of the motor or rotation of the motor to anti-clockwise or the clockwise. So these are all maintained or controlled by. So the important thing is you have to know that you need to have a digital to analog converter in order to get back the zeros and ones bit stream, which will be sent to the plant for its operation, correct? So now for each and every bits that is obtained at the CPU, you have a digital to analog. So here instead I can say it is a demux, wherein the information, the one single bit stream will give you a multiple outputs. Okay, so you have to have 3 DAC. If it is 3 information, that is pressure, and if it is temperature and the different voltage levels are the 3 inputs there at ADC. So we need to have 3 DACs here at the before it reaches the plant. So you need to have DAC, that is digital to analog converter, and then it would be the signals from the CPU will be sent to the plant. Okay, so DAC is connected to data bus. If you just see, the DAC is connected to this data bus, and the channels are selected by putting the channel address onto the computer address bus. So channel address will be selected based on the I/O at the CPU. So DAC acts as a latch. So this is a latch. If I consider 1, 2, 3 latches, so the latch usually has the information which is read earlier, and until unless it unlocks, until unless you get a new signal from it, right? The same way, DAC acts as a latch and holds the previous value sent to it until unless the next value is sent. Until unless the next value is sent, this value will still remain as 1. If it is 1 earlier, next until unless you have a 0, it still remains at 1 throughout. So it has been latched. Okay. So conversion time is about 5 to 20 milliseconds, and the analog output are -5 to +5. So minus 10 to plus 10 volts, or a current output of 0 to 20 milliamperes. So these are the values in which you are going to get the digital out, okay, from your from a digital out, zeros and ones here will be contradicted as voltage levels between -5 to +5, -10 to +10, and the current variation will be between 0 to 20 milliamps. Okay. So these are the required or accepted or wanted signals that should be given to the plant for its operation, because the plant will not understand zeros and ones, right? So again you have to convert all these zeros and ones bit stream into the respective voltage levels or the current measurement, okay, and then it will be sent to the plant. So this is about your analog output system. Next you have what is called as a real-time clock. We have already dealt what do you mean by real-time, what is its necessity, where it is implemented, details have been dealt earlier, right? So it's a vital auxiliary device for control computer system. It is very important because there is parallel processing, and time or a clock plays a vital role in talking about the performance of a CPU. It may or may not be a clock. Many systems, it's a pulse generator with a precisely controlled frequency. So it need not be always a clock. Even a pulse generator could, as I have told you earlier, a fixed duration of clock pulse could also be called as a clock generator. So AC supply lines is used to generate pulses at 50 times per second. Okay. So pulses are used to generate interrupts, and interrupt handling softwares counts the interrupts and hence keeps the time. So these are the how the actually the interfacing or how the clocks are generated. The interval at which the timer generates an interrupt and hence the precision of the clock is controlled by the count value loaded into hardware timers. So these are the ways in which the clock will be actually connected to the hardware timers. So the clock precision has to compromise between the timing accuracy required and the load to the CPU, because until unless you have the precision, for example, if you have a plant, if you are talking about a plant, then the plant which has a connectivity to a CPU means there should be a short distance, or you can say a parallel processing. If there is a parallel processing, then you need to have a very short duration of time to access the information then and there, correct? But if you're talking about a long distance, it is not possible. You can't have a parallel system there, right? Operation, right? So the clock precision, how precise is your clock? The on and off clock pulses comprises of the timing accuracy that is required to load the CPU. Until unless you load the CPU, until unless you get the ready and the acknowledgement signal from the CPU to the plant, the access will not be forwarded, right? That's the reason the precision level of a clock is very important, which should be accurate, okay? Small interval high precision with will lead to wastage of process time, not performing any other work. If you are talking about precise level, if I say exactly at 0.15 seconds, okay, 3 decimal levels, then what happens? Until unless you reach that precision level, the CPU will not be able to perform any other action. So what will happen? There will be delayed operation. So hence the clock pulse, if you are just talking about a clock pulse, the precision plays a vital role wherein it should be accurate, okay, so that it will not take more amount of time of your CPU to process it. If CPU takes a lot of time in the precision, then what happens? There will be a delayed processing. So disadvantage of real-time clock: the clock stops when the power is lost and the restarts. Current value of the real time has not been entered. So what happens? There is a drawback in clock, okay. So as soon as the power goes off, what happens if there is no power and the operation has just begun? The clock cycle, again it has to repeat by itself. So there is a waste of time, isn't it? So the disadvantage in real time clock is clock stops when the power is lost, okay, and restart, and it has to again restart from the beginning. So there is a wastage of time, okay. Real time can be read from a card, okay, and card can be programmed to generate an interrupt to a specified frequency. So real time clock, computer manufacturers have different kinds of timing, real time timing that they actually embedded in a external or an add-on card, which will be connected, right? But it would not be the same for any other system. That's a drawback again, right? If you have a real-time card, which is specified for certain duration of time, it will not be same for the rest of the other systems to operate with the same card, okay? So if you have a programmable, or if you have a modular way of obtaining a card, then it will be more easy, okay. The only thing is you need not have to change the system, you can just change the card alone, okay. Units are supplied with battery backups so that even in the absence of the main power, the clock function is not lost. So now there are a lot of advancement where even when the power goes off, so since it is programmed, the clock function, the timing of the clock will still remain as it is, and then it restarts again. The best example is when there is any mismatch in the processor and the external unit, what will happen? You have the complete CPU starts resetting, it tries to reboot itself, correct? So there is a recheck procedure, okay. So until unless it reaches 100%, you will not be able to go ahead and shut it down. It says that I am starting to reboot your system, right? The same way here, what it is trying to make sure that the clock is not lost during the operation, Okay. They are used in batch processing and online computer systems. Slicing techniques is used to avoid delay. So, this is one of slicing techniques helps in reducing the delay, because it will just take one level of signal, and it is not just and it is applicable for all the batch processing. We also already know that what is a batch processing. Computer programming, or you can say computational level of your CPU in a better or a higher performance level. It will take to a better or a higher performance level. After knowing this, you have what is called as a data transfer techniques. Okay. Data transfer is between the interfacing device and the computer. So, you have an interfacing unit and you have a computer. Okay. So, standard I/O units, okay, and your computer, how is the data being transmitted from those two, between those two units. Okay. Program transfer control the data directly and involve CPU, and DMA, that is direct memory access. What happens as soon as there is important interrupt, so immediately the without even wasting any time, what will happen, there is an alternative approach where the data is transferred between the device and memory without even disturbing your CPU. So, without disturbing any processing event that is occurring, it directly gets the information from the memory, and the device will be able to interface it. Okay. That is about DMA. So, these are all the basics that you have learned. So, in the next class we shall study about what is the interrupts, different kinds of interrupt levels. Okay. Thank you.